In this part of the tutorial, we'll learn how to use PSpice to create Thevenin's and Norton's equivalent circuits. And just go ahead and create a new project called Thevenin. Make sure analog or mixed AD is selected. Create a blank project. Okay, very good. Just go ahead and zoom in once. And just go ahead and use place our parts. I will use the bar right here, so that's easy to use for me. We need 5 resistors. Two, 3. Rotate this one. 4, and we'll have this one. 5th one. Okay, very good. Right click and mode. Okay, now we need a voltage source. VDC. Okay, we need to mirror it vertically. Put it right here. Okay, now we need also a current source. IDC. Okay, I'll rotate it as well. I'll put it right here. Okay. Hit escape to exit the mode. Just put the resistor in the same level. Now we'll wire them. Hit the wire right here. Now let's just go ahead and enter the values. This will be 3. Let's just go ahead and create a new simulation profile. Okay. We need to select bias point and apply. Okay, now let's go ahead and run it. So simulation is complete 100%, and we'll see the voltage here. Okay, we can see that the voltage is 4 volts. So, but now let's use our Thevenin's circuit to find this voltage again. So what we do in Thevenin's, Thevenin's theorem, we just take out this resistor R4 and measure voltage there. So let's just go ahead and do it, and by measuring voltage right there won't work simply because we just got error here, so we don't have connection here. Well, let's just go ahead and simulate our open circuit with a large enough resistance. So actually here is pretty good thing that memorizes all my selections, and I can access R from here right away, nice and fast. So let's just rotate it and put it in here. Okay, and we need a exit mode. So what we're gonna do, we just gonna put a large resistance like 500 mega ohms, for example, 500 meg. And I wrote meg here because PSpice is not a case sensitive, so and the suffix m is for milli. Actually, the suffixes are pretty much the same, like P stands for pico, N stands for nano, and except for, like I said, meg for mego, and we have also in PSpice we have to use U for micro because, well, we don't have mu here, and PSpice is not case sensitive. Okay, let's go ahead and run our simulation again. Okay. And take a look at okay, V Thevenin here is 8 volts. Now we need to find R Thevenin. Okay, how we're gonna do it? We'll just get a resultant resistance by taking out our current source and voltage source. So first I'm just gonna copy this real fast. Okay, and now we have to, when we take out current source, we just hit simply delete, and we need to substitute it with an what's gonna be an open circuit. So okay, and then our voltage source will be taken out, and we just short circuit it. Okay, and then instead of this resistor, we will just put a current source of 1 amp. So we'll measure voltage across this current source, and voltage divided by current, which is going to be 1, is going to be our resistance basically. So I'll just go ahead and place the current source right here. Okay, hit escape. A little bubble like here, yeah, we just need to take care of it. Okay, let's go ahead and put 1 amp. Okay, let's go ahead and run the simulation. And we'll see the voltage here across the our current source is 4 volts, and our resistance R Thevenin will be 4 ohms. Okay, let's go ahead and build a circuit. I'll just delete all that stuff, and we'll just go and create a VDC. Yeah, let's go ahead and enter values. This is going to be our 8 volts and our V Thevenin. This is our R Thevenin, which is 4, and the load resistance is 4 volts. I mean 4 ohms. So let's go ahead and run PSpice. Okay, let's see voltage. Oops, the voltage here across R2, which is was our target resistor, our load resistor, is 4 volts. So that's how we solve the problem using our Thevenin's equivalent. So, and now let's go and do it for Norton's. Here I just recreated our initial circuit, and according to Norton's, we'll have to take out this resistor and measure current in a short circuit, short circuit. So let's go ahead and do it. Our simulation is complete, and we're now interested in the current, and the current's gonna be here 2 amps, so we'll have to run it right here. So now let's go ahead and create our Norton's equivalent circuit, because we already know that our R Thevenin is actually 4 ohms. Okay, getting current source, rotate. So as you see here, our load resistance is gonna be in parallel with our current source. So the load was 4. And the load resistor is 4. Okay, let's go and run PSpice now. And let's see the voltage. And the voltage there is 4 volts, which makes sense. In this part of the tutorial, now we will learn how to apply sinusoidal and pulse input signals. A variety of signals can be applied to our circuit. So far, we have dealt with a DC source only from our menu after we create our new file. So we need to select vSine source. Okay, let's go ahead and select vSine. Okay, let's also, after we put a vSine, let's also put two resistors in there. So, just to keep our circuit fairly simple, this is going to be one, and this is going to be the second one. So let's go ahead and put 5 and 10 ohms to keep our circuit, as I said, to keep it simple. Now let's go and wire our circuit. Okay, now we have 3 parameters at our vSine, so we need to input the values for them by double clicking each of them. So V off, that's the time of offset, so we put it 0. V amplitude is our basic amplitude, which will be 15 volts, and frequency will make it 1 kilohertz. Now let's create a new simulation profile. Let's call it pulse. Hit a button create. Now we will need to select the runtime to 2 milliseconds. Okay, hit apply and OK. Now let's select our voltage probe, and we'll put it right over there to look at our voltage across 10 ohm resistor. Now let's run it. So as we can see, we have our sine source. Let's now select trace, cursor, and a mark within the display. So now we can see the cursor going along our sine wave, and we can left click our mouse and move it back and forth. Here you can see a probe cursor window where the values change, and we actually can put our values right on our graph by clicking it right over there. Here goes one, and here goes, for example, another one. Okay, now we can let's apply pulse source to our circuit. Let's go select vPulse. And we can insert it right here. As you see, vPulse actually has 7 parameters. Let's put the values by double clicking each of them. So V1 will be our lowest amplitude, which will be negative 15 volts. Our highest will be 15 volts, so we have like a sine kind of wave like we had with an amplitude of 15 volts. So TD is a time delay, so we put a 0. TR is a time of rise, so we'll just put it 0 to have perfectly square one, and TF is a time of fall, so it's gonna go down in at a straight angle, and we have PW is a pulse width, which should be half of the period. If you want to do a square wave and the period is 1 millisecond, to have it like 1 kilohertz. Let's run our simulation. So we see our actually time of rise and time of falls are not exactly at a straight angle. So we'll go to settings again, right over there, and enter maximum step size of 1 microseconds. Hit apply and OK. Now run simulation again, and now we can see we have fairly straight lines over there and pulse signs. So this is pretty much concludes our tutorial.